over 4 minus 2 brackets
and we had to find where it's concave and convex. Yeah. Is that correct? Right, yes. Okay. Right, I apologise for that. There we go. So here we go. And Beth, I don't know if you've caught up with the video.
Yeah, was it the one that you sent at like
yeah, that's right. Yeah. So we need to differentiate this and then differentiate it again. So Harry, tell me how you're going to do the first differentiation.
3 times. So 2 times 1 within -4.
It's not -4. If you think of this as x over 4, another way of writing that is a quarter of x.
Oh, yeah.
So it would just be a quarter. So I'm going to rewrite that as 3/4. And then Grace, if we differentiate again.
Oh yeah, so it's 3 over 16, isn't it?
I'm going to multiply by the power, so 2 lots of 3/4 is 6/4 or 3 over 2.
Oh, right now.
What's the power going to be? And then multiplied by a quarter again, that's right, yeah. So that gives me, is that what you're trying to tell me? Sorry. It gives me that. With me so far? So I've differentiated using the chain rule, that's what we call it, although I don't really sort of think of it as the I don't know. 3/4 and then 3/4 times 2. Yes, we do. Right, that's okay. And so we're asked where this is concave or convex. So I'm going to start by asking where it equals 0, and then I know that either side of those points it will probably be concave or convex. When the second differential equals 0, that's when it changes from going like that to going like that. So remembering, Pat, that 0 is your friend, what can I do straight away to make this much easier?
times by 8?
Times by 8, yeah, and divide by 3. Okay. So I can actually get it just to that. And, you know, it's quite easy then. We just... So I know I have a point of inflection at x is 8. And so all I need to know is either side of that, is it going to be concave or convex? So I'm going to use a nice easy value below 8. So this is my second differential here. So when x is 0, that's -2 times 3/8, so that's negative. So it's second differential is negative then. And I'm struggling a bit to remember what that means. So negative means the gradient is getting smaller. So that's like this, isn't it? So that is concave. So it's concave below 8 when x is less than 8. And then I want to choose a value that's bigger than 8. I can use any value I want really, but if I use 12, then here I've got 12 divided by 4, which is 3. 3 take away 2, which is 1. 3/8 times that, that's positive. And that means it's convex everywhere after 8. So 8 was our point of inflection, and then we just had to work out what was it either side? Was it that way round or was it that way round? And we did that just by looking at the sine of d2y by dx squared. Concave if it's negative, convex if it's positive. Great. Okay, so today I want to carry on using the chain rule. And I want to introduce you to 3 new things to differentiate. And because time is a little bit short, I'm not going to justify how it works. I'm just going to say, when you differentiate this, this is what you get. Okay? When we first introduced differentiation with powers of x, we did first principles, and you can do that for this, and it may be that we have lots of time and we have the time to do that. It probably isn't the case, so we're going to get through as much as we can. So if I just remind you where we started, we've said, okay, if y is equal to something like that, I can differentiate that. And if you've got a coefficient out the front, well, I can differentiate that as well. The 2 is just sat there, so I get 5 times 2, 10. And then yesterday, I introduced the idea of something a bit more complicated to the power of 5. And we use the chain rule. We say, okay, dy by dx, I multiply by the power and reduce the power by 1, just like I've always done. But because that isn't just an x, I've then got to multiply by what I get when I differentiate that, which in this case is 2. So you end up with... And lastly, if we've got a coefficient out the front here, well, all that does is it means that, you know, I've got 3 times 5 to start with, so that's 15, and that becomes 30. So just 3 times as much as that. So that coefficient sort of passes through unchanged. Okay, so let's meet the first new thing that we're going to differentiate. And it's a thing we've already spoken about, actually, and differentiated it before. So I suppose it's not a new thing, is it? But there we go. E to the x. Y equals e to the x. So you may remember that, you know, 2 to the x and 3 to the x and 4 to the x, these are all things which are growing. But if it's growing with a multiplier of e, 2.7-ish, has a particular principle, its gradient is the same as the function. So dy by dx, when you differentiate e to the x, you get e to the x. And if there's a coefficient in front, well, that just stays there. And we can also use the chain rule, because if it's not, sorry, I should have left a bit more space. If it's not e to the x, if it's something like e to the power of 3x minus 5, for example, I mean, don't really need brackets there, but I'm going to put brackets there. Well, we use the chain rule. We say, okay, so I know when I differentiate e to the power of something, it doesn't change. But because this time the power is more complicated than just x, I have to multiply, and I'm not multiplying up here, I'm multiplying the whole thing by what you get when you differentiate that, which in this case is 3. So I get 3. And if there's a coefficient out the front, well, that just multiplies through. So rather than that being 3, it's going to be 3 times 5, so that'll be 15. So when I differentiate e to the power of something, the power never changes. stays the same. So can I just get you to differentiate a couple of E expressions for me? Oh, this is so big. So I'm hoping you've got 7 e to the 7x plus 1, because it's just e to the 7x plus 1 multiplied by what you get when you differentiate the power, which in this case is just 7, the 1 disappears. So e to the 3x becomes e to the 3x multiplied by 3. So 4 e to the 3x is 4 e to the 3x multiplied by 3, so you get 12 e to the x. Third one, 2 separate terms, so we do them separately. X squared, just like we've always done, is 2x. And then here, a little bit fiddly, I've got minus 2 e to the minus x multiplied by what I get when I differentiate that, which is minus 1. If you differentiate minus 1x, you get minus 1. So actually that all becomes plus 2. You've got minus 2 times minus 1, so that's plus 2 e to the minus x. And then the last one, yeah, power doesn't change, multiplied by what you get when you differentiate the power. So I could leave it like that, or I could write it like that. Probably a bit nicer, isn't it? But that's just the chain rule. We're taking the basic rule, just like we did yesterday, and we're saying if that isn't just a single term, if it's something more complicated, then we differentiate it like we've always done, but then we multiply by what you get when you differentiate, in this case, the power. Okay, the third thing then that we use, that's sort of new, is ln of x. Now, ln, if you remember, is log to the base e. We can't differentiate any other log base. We can only differentiate easily, anyway, ln of x, and that's one of the reasons why we use e and log to the base e, because it makes it easy to differentiate. And it's really easy to differentiate. Again, we could prove this by first principles. We will do in If you want to hang around after the exams in the summer, we can go through all those things that we don't have time for, but yeah, it's just this, 1 over x. I mean, you can sort of see it from the graph. So the graph of ln x looks like this. And if you think about, dy by x is the gradient. So think about what's happening with the gradient here. The gradient's really big and steep and positive here. And what happens with ln x is it gets less steep, but it never becomes negative and never flattens out. So if you think about what that looks like in terms of a line, so it's very, very positive here, but it never becomes 0, and that's the graph of 1 over x. So that's the sort of a sort of pseudo proof, if you like. Right. So what if you've got a coefficient out the front? Well, you just get 3 times that, which I'm going to write as 3 over x. And what if it's something a bit more complicated than just ln of x? What if it's the ln of 3x minus 5, for example? We use the chain rule. dy by dx is 1 over, well, when it's ln of x, it's 1 over x. So in this case, it's 1 over 3x minus 5 multiplied by, surprise, surprise, what you get when you differentiate that, which is just 3. So that gives you 3 over x squared minus 5, sorry, 3x minus 5. And if I've got a coefficient out the front, well, it's just going to be this answer multiplied by 2. So instead of 3 over 3x minus 5, it will be 6 over 3x minus 5. Remember, when you multiply a fraction by 2, that's like 2 over 1. So it's only the numerator gets multiplied, the denominator stays the same. So let me just give you a couple of ln ones to differentiate. Just see if you can differentiate those 3 for me. Now, the middle one, you do get a slightly odd result. You may notice it. don't know if you noticed in the first one, so you get 1 over whatever's in the bracket, 4 minus 2x in this case, but then you multiply by what you get when you differentiate that, which is minus 2. So that gives you that. And we can only do this if everything can be divided, but in this case, everything can be divided by 2, can't it? So I get a minus 1 over 2 minus x. Now, you know, if you didn't notice that, it's not hugely critical, but yeah, you can take it as far as that. And you get a similar bit of cancelling with the second one, because you get 1 over 3x multiplied by what you get when you differentiate the bracket, which is 3, which gives you 3 over 3x, and you can divide those two by 3. Now, so what's going on here? How come that the differential of log of 3x is the same as the differential of log of x? And the same is going to be true for any multiple of x. You know, 2x, 5x, 7x, whatever. That's something I will return to. Maybe today, maybe another day. But yeah, there's a good reason for it. And some of you might be able to see the reason, but I'll return to that. But it does cause us a problem when we integrate, because obviously integrating going the other way. Ln of x squared, so you get 1 over x squared multiplied by what you get when you differentiate x squared, which is 2x, so that gives you, surprise, surprise, bit of cancelling again there I can get. Which is the same as what we'd get if we differentiated 2 ln x. And, well, again, we'll return to that. I mean, it might be obvious why that's the case. It might not be. That's not a huge problem at the moment. We can talk about that. Let's do a couple of questions, though, at this point. So, you know, we're slowly sort of spreading the net of things we can differentiate. So we can now differentiate just about anything that includes a power, including 1-overs, because they're negative powers, and square roots, because they're fractional powers. And now we can differentiate anything that involves an e and anything that involves an ln. So have a go at this question, which is from the Pure 2 textbook. It is on page 236. I know I haven't brought them in, but I know some of you might have a look afterwards. So that's page 236, that question. So it's a standard find the equation of the tangent to a curve. So you're going to be differentiating, substituting the value of x in, 1 in this case, working out the gradient, then working out the y value, and it's a show that, so you know what you're aiming for, and it's obviously not super nice and straightforward. But start by differentiating. And this is a good question because it involves both of the things we've looked at. So I don't know if you want to check that you've differentiated it correctly. So e to the 2x multiplied by what you get in the brackets. Next, and the value is 1. For the point, you need to go back to the original function. That gradient looks horrible, and I'd be upset by it if it wasn't for the fact this is a show that question, and that is the multiple of x, so I know that I've got the gradient right so far. What's the good news, Pat, about ln of 1? Type it on your calculator. Just do ln 1. 0. So that's my coordinate. So that's nice and easy, isn't it? It's a little bit fiddly. We've got to do a little bit of E arithmetic. We mustn't be scared of that. It's funny really, this is really hard A-level maths, but we're not really doing sums, are we? It's almost like we're writing a language rather than actually doing any calculations, because so much of it is left in terms of E and ln. So, so I differentiated and substituted in the value of x to get the gradient. Didn't work it out, just left it in terms of E. I worked out the point. I worked out the value of y when x is 1, left that in terms of e and log, although the log disappeared because the log of 1 is 0. Substituted it in, left it in terms of e. When I got here, I just took 2e squared from both sides, so I ended up with a minus e squared there, and added 1 to both sides. That gave me my c, and then I just replaced c with that, which is exactly what I was being asked to do. So that's quite nice that that all ended up okay. Let's just try one more of this type then. This is on the next page, page 237. So here they tell you the gradient is 2, and you've got to work out, or you've got to sort of do some calculations about the point where that happens. So work out dy by dx. make dy by dx equal to 0. That's what we're after. Sorry, equal to 2. Equal to 2. So what they're saying in that middle sentence is that when the gradient is 2, the point where that happens, the x coordinate is a. So what I'm going to do is I'm going to do two things. I'm going to make that equal to 2.
So, what about the plus 4?
When I differentiate, that disappears, doesn't it, when you differentiate? Yes, so constant terms just sort of disappear. So I'm gonna ask when does that equal 2, but I'm going to replace x with a as well. So I'm going to do this, and so basically I'm going to try and make that equal that. That's what they're trying to make you do, and it sort of happens quite quickly. They've done what I would do. That's how I feel about fractions. That's the first step. So what was your first action? Isabel B?
Times by A.
Multiply everything by A. Now that here just means you get 2A times that. Now, because we're aiming for that, everything with an A needs to be on one side. So I'm going to take away my 2A and add 2 to both sides. At some point I can divide by 2, you may have already done it. I'm going to divide by 2 now. Remember, everything by 2. Not that's that doesn't get divided by 2, that's the power, that's not a multiplier, and then it falls out quite nicely. So it's a bit weird because, there's so much that isn't numbers. It's an awful lot of E's, an awful lot of LNs. And, for some people that makes it easier. Other people are much happier, with a decimal in their answer or something like that. But no, this is what we need to get used to. Let's just briefly go back to the two funny results we got with log. These two here. Let me remind you about the log rules we talked about. Could anyone suggest how I could use the first log rule in reverse to rewrite that? The first log rule is that log of A plus the log of B equals the log of AB. So how could I use that in reverse? Yeah. Now the ln of 3 is a constant, it's a number. There's no variable involved there. And we know when we differentiate, constants disappear. So differentiating this, well, we said that if I differentiate that, then I get 1 over 3x multiplied by what you get when you differentiate that, which is 3, which all cancels down to 1 over x. Well, if I rewrite it like this and differentiate it in that form, well, that disappears, because when you that's like the 4 in that previous question. When we differentiated, it disappears. ln of 3 is another number. It's not a very nice number, but it's another number. So that bit differentiates. So it's the same thing. So, it's not surprising that we get this. Now, how can that be? What we're doing is we're working out the gradient of a function. Surely, changing it from ln of x to ln of 3x will change the gradient. Well, actually, it doesn't. Here's my graph of ln of x. If I change that to ln of 2x, what I'm actually saying is, or ln of 3x, sorry, I'm saying, well, okay, that's the same as the ln of x plus the ln of 3. If I take that function and add something to it, it just shifts it up. So the gradient at every point doesn't change, it's just been moved up. So that's why, and you don't need to worry about this, okay? I just always like to try and justify things. It is not surprising that those two things give us the same result, because you can rewrite ln of 3x as a constant plus ln of x. And that's a useful thing to remember in other places as well. Show that questions. You might get an answer that's got ln of 3x in, but they want it in some form with ln of x. You think, oh, I've done it wrong. Well, actually, no, maybe splitting it is the secret. And the other one which gave us a slightly odd result, was ln of x squared. Now I can use my third log rule in reverse here, because you may remember that the log of a to the power of x is the same as x times the log of a. So in this case, that means that's the same as that. And we use that all the time in other places, but those two things are the same. And so when I differentiate this one, then I get 1 over x squared multiplied by what you get when you differentiate the power. And I can then cancel out an x. But if I differentiate this, which is the same thing, then I just get, well, that's 1 over x, so it's 2 lots of that. I get the same answer. So again, it's not surprising that this gives us the same answer as this when we differentiate, because they are the same thing. It is 2 different ways of writing the same thing. So maybe in a show that question involving ln of x squared, where they want it written in terms of ln of x, you think, oh, I've done it wrong. But actually, no, you can rewrite that in that form, and all is good. All is good. There's one other which we didn't come across, but if I was asked to differentiate this, well, that looks a bit unpleasant. So here's what I'm going to do. I'm going to say, oh, well, actually, 1 over x is x to the power of -1. And I can then use that third log rule to write that as -1 times the log of x. So the differential of that is just -1 over x. And that's a lot easier than trying to get our heads round this. You'll get the same answer if you differentiate it in that form. 1 over x multiplied by what you get when you differentiate 1 over x. But it's much easier to think of it in that form there. It's the same thing, so differentiating that is the same as differentiating that. Okay, so we are galloping through differentiation. We've done powers, we've done e's, and we've done logs. So the next thing we're going to do on Tuesday is trig. We're going to differentiate sine, cos, and tan, and we're going to apply the chain rule to that as well. All good. So remember, the assessment next week we'll do on the Friday. So in the Thursday lesson, you'll get 10 minutes and a blank I Love Trig sheet to sort of, and form the book to sort of fill that in, and you'll then be able to take that into the exam. Good stuff. I hope you have a lovely weekend. Well done for battling through this week. It's been a bit of a weird one.